Welcome back, everyone. I guess I'm going to chair this first afternoon session. And welcome our speaker, Rachel Soto-Garcia. She is starting at Rensselaer Polytechnical Institute, RPI, in the fall after doing an REU here with Professor Baronis, Electrical Engineering Department. And so continuing this theme of using things like machine learning, neural networks, applying that to quantum problems. She's going to be talking about what you see up there. So it has the makings of an interesting talk.
Yes. Thank you. So hello, my name is Rachel Soto-Garcia, as you mentioned. So my topic is going to be evaluating the automatic classification of a Laguerre Gaussian mode using deep convolutional neural networks. So before we get into it, we're going to look at an outline, overview of everything. So we're going to start with the introduction, we're going to talk about machine learning, and we're also going to talk about the simulation setup, the results, and the acknowledgements. So for the introduction, we have a few things to get through because I don't know if everyone knows everything, because for me, this was all new. So for the Gaussian beam. So this is a really special type of beam that has a special property of, it's a single frequency radiation beam. So what that means is that it's really big here, and then it gets really narrow, and then it expands again. So like a convex lens, if anyone knows what that is, the image is like normal, and then it gets really small, and at focal point, it switches, and it gets really big. So this does expand. That's a special characteristic that it has. And it can create three types of modes. So we have the Hermite Gaussian mode, we have the Laguerre Gaussian mode, which we're going to speak mostly about, and then we have the Inca Gaussian mode. So the thing about the Laguerre Gaussian mode is that it helps a lot with transferring optical information. So this is why we really want to talk about this, because this is how we want this to be implemented in optical information, transferring optical information. So here's the experimental setup that we have to create the LG images and the LG modes. So right here, we have the laser beam. And so a laser beam, we didn't have a bunch of space, so we have to use the mirrors to optimize the space that we have available. So it goes through here, and then it goes through the fiber. And the fiber allows it to, so we can put it in a certain frequency. So as it goes through the fiber, we pick the frequency, and the wavelength of the frequency was 633 nanometers. And then it goes through the lens, so we can pick the size, with what size we want it to be. So it goes through the mirror, hits here, the SLM, and this is how we create the mode, like what mode we want specifically. And then it goes through the lens again, and then we take a picture of it.
So, which lab is this?
This is for William and Mary University. So this is their lab.
Oh, okay, so you were not in the lab yourself? Okay, but you're working with people there? Okay. And what is SLM?
So this is the spatial, I believe.
Spatial light modulator?
Yeah,
okay.
light modulator, yes. So these are the images that we had during the experiment. So as you can see, we didn't have LG33. Also, this is a different image because they didn't provide us with LG03. So we had to take it from old images that we had back when we started doing the project. So these are all the images. And also for LG32, we didn't have all 1,000 images. Oh, so all the images you see here, it's basically 1,000 images we have. So this is going to be our test data that we're going to use. And we have only 622 images in this one.
Sorry, the modes are indexed by two symbols, L and G?
L and G. So, we're gonna go through when I get to talking about the machine. So why do we need machine learning? So as you see in these images, these modes are very they can be very similar and how they look and everything. So why do we need it? Why is this so important? Why do we need machine learning? So recognizing these modes are difficult because they're so similar, and there's so many. There's like a limited amount of numbers. So and the image can also be noisy. So in this, right now, do you know which one is LG23? Unless you're an expert with the LG modes, you probably don't know what it is. So this is why we're gonna use machine learning. So what is machine learning? It is part of the artificial. It started with artificial intelligence, then going into machine learning, and then we're gonna be using deep learning especially. So it starts off artificial. Does anyone know what artificial intelligence is? Or everyone? Yes. So yeah. So this is where machine learning branches off from. So deep convolutional neural networks. So this is how we're getting our system to realize what image is which, where it goes and everything. So we start off with like an image, and it goes through pooling and everything. So a computer can't read an actual image. So we make it into numbers. So each particle or each pixel gets a number, and that's based on the color. So it could be in grayscale or like whatever the image looks like. It's given a number, and then it goes through pooling. So then we take a group of numbers, and then that using a matrix turn it into a different number. And it looks for patterns. And if it sees like this white background has the same number, like it's like 0, 0, 0, they get rid of it because there's no use in the image. They're looking for patterns in here, what makes it unique. And that's why we're going to be using it to identify the LG modes, because there's unique patterns to some of them. So there's a lot of CNN modules that are provided. The first one invented was LNet 5, and we are using Inception v3, and each of them have their own special things and their own special features. But for this project, we thought that this one would be the best. But we're even looking at different modules because we're not sure yet. But each of them have their own special features. For example, VGG is very good with very good and very accurate, but it takes a long time to run because of it. And LNet 5 right here, it's great and it's very accurate, but it only works with like very tiny like images. So the short
what do you mean by tiny images?
So it only does 32 by 32 pixels.
Okay.
And our images are 300 by 300. So it wasn't very good for us to be, okay, let me try that because it has a good accuracy. It wouldn't work out because our images don't fit that criteria. So the overview of the code. So we have two major parts to this code. We have the training and the testing. So we have 1,000 images. So we put 80% of those images into training, and then we hide the other 20% so we could use that for testing it. So the computer didn't see these 20 images, and we're just gonna re-see, okay, did you really learn this? And the training is based on two important parameters, epoch and the training rate. So this is like how many steps the code can take. So how many pixels is it allowed to move, while the training rate is how many times is it gonna go through. So now we are going, and then we just ask it, we test it and everything. So how am I gonna show you my data results? So we have the confusion matrix, which is a common way to show CNN results. So here is an actual example. So we have 13 sample sizes. We have 8 cats, 5 dogs. The actual classes was a cat, and it guessed cat. So like as you can see in the red, this is when it's right, when the machine got it right. And the white here is when it's not right. So as you can see, we want these numbers in the middle to be higher than these numbers. Preferably, we want them at 0. But not all codes can do that. Nothing's perfect. So the simulation setup. So this is where what I mainly did in the project, our simulation setup, samples and results of the training with deep learning. So we had 15 modes, as I said earlier, and because we were given LG33, and L and G were changed from 0 to 3 independently. So as you saw in the first image, it had L like going down, it had G going down. So depending on how you went, they all are different modes. So there's 9.
I have a question.
Yes.
What characteristic is L telling us, and what characteristic is G telling us for the Laguerre Gaussian modes? like they had certain structure.
Yes. So that's actually going to be seen when we go through the simulations and when we went through deep learning. You're going to
Okay.
see something did happen with that. So as you can see in the setup right here, LG0, when you're going across with G, there's different rings. You see how the rings are all forming? As
Yeah.
you go down with L, it's the size that really changes. It's just how it
Okay,
expands.
thanks.
So you'll see something with it when we go through the simulation with the deep neural network. As it went through. So in the simulation, we did 9 simulations. So we went row by row, column by column to see where the machine was getting confused. Because we didn't want to just do one big full simulation and be like, oh, it's not right. Where did it go wrong? So we did a bunch of small simulations with it going across and down the rows and columns. And it all depends. We had simulations with 3, 4, and then 16 because we wanted to do all of them at the end. And then we had some sample sizes were ranging to like 4,000 for each simulation. And all the size images were 300 by 300. And the sample sizes, like in total, we had 3,500 images. So, and this is how it looks in the code. So, for me personally, we put it in, or the way we knew what LG it was, LG mode, we put it right here, and then this is the number of what image it was. So this was image 66, and this is when it guessed. So my machine guessed 65% with confidence that is an LG 32. It was right. And here on the side, you can see how it was like, oh, I also guessed it's LG 12 with 23%, and it's LG 22 by 6%, and LG 02 by 5%. So this is the confidence that the machine had and the patterns that it also recognizing in the other LGs.
It's interesting that it was positive that the G was 2. It just didn't know what the L was. And you were saying the L is the size parameter. So I feel like that makes some sense because you can see how many ridges there are. Yeah, okay.
Results. So simulation 1 through 9. So here we have that G would change. And it was pretty good. It was pretty good. And also, because we did 20%, realized that this is only going to be 20. We didn't have all 1,000 images. We only had 100 for this one, so that's why that one's 20. But it did get confused when it came here. Because it was so closely packed together, the machine does get confused. So we can see how this was correct. And it's pretty good. LG, it can recognize the difference here. Once it gets here, since the rings are so small and there's like a little bit of noise here, it does get confused. But it's a pretty good reading. And then we have LG. Now we're going by size.
So wait, wasn't it a perfect reading? Oh wait, I missed the 27.
Yes.
Okay, that was the one.
That's,
Okay, I'm
see,
sorry.
like, it's really good here, but then it gets confused right here.
It's just that one point of confusion.
And right here. Now, this is where we have a little bit of some issues. We have some issues here. And this is because it's going by size. You'll see later how there's a bigger difference. But here you can see the size, see how it's just growing a little bit, and it had had errors here. But if we go on to another one, this is all based. These look exactly the same. If you look here on the side on the image, even though there's a slight difference in size, a deep neural network is supposed to look for patterns. So as you can see, it wasn't that great because they look the same. They all look the same, going here, here, and here. So that's why the system had trouble, because it's like, okay, I know that's that, and I know that's that, and I know that's that, and that's why. And it trains with LG1 first. So that's why it has a big bias towards LG1, because it was training with it first. So it has a big, strong, okay, I'm pretty sure it's this. And that's where we could find the mistake, why it's having a problem. It's because there's a size difference, it can't really explain, it can't see the pattern. If it was like a lot bigger, yes, it would be able to see the pattern. But since they're so closely packed together, they almost look identical. So I
will expect the 1, 1 be a larger number because 0, 1 and 1, 1 are more similar inside. However, the larger number is the 3, 1. That is larger than the 0, 1.
This one and this one, yes.
Yeah, no, yeah, and this does not agree with the first column you are showing. I mean, this is an example, I suppose. No?
So yeah, there is a little bit confusion because here, but they're also when you're pulling with the pixel, how we set it up, the steps, they're a little bit bigger. If we maybe made it a little bit smaller, the steps, because all the steps are the same, we kept them all constant, that could be the reason why. Because since they're a little bit bigger, the machine has trouble like, okay, well, since they put the matrices in one like big blurb into one number, that's why that could have the same value. So that's why this could be that's why the machine gets confused. So maybe if we change the setup with the steps it took for each matrice, it could also explain why it could also have a better result.
What's the difference between the validation set and test set?
Okay, so the training accuracy and the validation accuracy. So when it's going through training, it gets tested. In the training system, it also does its own little test with 80-20%. So it's going through the training accuracy. It's like, okay, when it's getting training, it's testing everything. It's like, okay, it got it right, so it's 100%. And validation, it's when it keeps doing it over and over again, and it just validates it like, yes, this was accurate by a good margin.
Maybe you should open a little bit. What do you mean for 80%, 20%?
Okay, 80%, 20%. So when we gave it,
Give an example.
okay, so yeah, so an example would be that if I had 1,000 images, I kept 20% of it. So I kept 20 images, or 1,000, so I kept 200 images, and 800 went to the system. And then from the system, it took 8%, 20%. So it also did, I'm gonna keep 80% of the pictures, and then I'm gonna test it again. And then it keeps redoing it with the 20% it did keep. So it's going over the same 20% over and over again to see, okay, can I make this better? Can I redo this over and over again? Did that answer your question?
Did you try cross-validation?
We did not try. Well, I think it was in the system, but we didn't write it down. So now it's
Sorry,
this
question. So if you go back to the number 2,
two
what does it mean when the training accuracy is lower than the validation?
accuracy. So for do you know?
So, should we go there?
You can.
I'm at. So imagine I have 100 images. Is this much? First, I'm going to cut it to 80. I keep this 20 something. I'm not going to show it to the system. I give this 80 images to the system, and I name it train. System by itself again cut it to 80-20 for itself, and I start to train itself. So says, okay, I keep 80% of this 80, train myself, then go pick one of these, check how much I am accurate. Now the system knows what is this one, because I gave all of this to the system. I label each of them, tell them, okay, this is 0, 0, this is 0, 1. The system knows. So here when the system picks something, just want to test itself, say, okay, for example, I don't know what is this. Let me see, can I guess based on the first training I did? Then says, okay, I guess correctly. Good job for me. Let's go do it again. Is do all this circle until by itself guess all of them correctly, or as much as it can. It means as much as I gave it the freedom. What do you mean? For me, as a freedom means when I do the system, when I design a system, I have some part. First I go to write some part to give the data. Then for the second part, I should normalize my data. These steps are very important. Normalization is very important. What do you mean by normalization? Normalization means, for example, when you change this image to the number, it goes to from 100 to thousands. But when you change this image to number, it goes to 1 to 200. So they are not normalized. System will get confused. So I have to write some part to say, okay, change all of them between -1 to 1 to let them to be all in the same level. So I put the data, I will design how to put the data, I will design how to put the normalization, then I call a model, which was the model Rachel shows like Inception V3 that she talked about it in more detail. In the model, also, I have to tell the system, okay, you have freedom. I will give the system some parameter, like for example, epoch, that you can go repeat this up to like 5,000 times. If you feel that you find it on 500, you're okay. But you are free to go up to 5,000. Or I get the system, I have to design for the model that if this is my image and I want to design the hidden layer, go to hidden layer, Rachel. And here. And you want to make it this hidden layer. These are hidden layer inside the system. So what that means, hidden layer means I go to the system, okay, this is my image, cut it this much, and make the matrix based on them, and apply like a ReLU function on them, and after that again cut them this much. Why is important? Because like for example in our image we have a lot of blue part. Why we need to spend time on blue part a lot? So I pick this step very big to catch the main picture. So let's back here, I do the model, then we go result. So let's back here. So we did the model. System train itself. So first did train itself, which is that training. Then get validation train, which how many it can choose correctly. So maybe it cannot go by 100%. That's why these numbers are different. Then I'm going in test part, release this 20%. Now system doesn't know what they are. There is no label on them. So system start to guess. And now completely based on the train we did. And say, okay, let me see what is this, and what is this, and what is this. And system can see each of these images just once. So this is how it works. That's why we have these three numbers: training number, train accuracy, test accuracy, and validation accuracy. It's better to say train accuracy, validation accuracy, and this test accuracy. Train accuracy, validation accuracy, test accuracy. So,
If the validation accuracy is smaller than the training accuracy,
yeah, it might happen.
It means you don't have enough images?
Yeah, maybe we don't have enough images. Maybe the epoch wasn't right. Maybe the training step wasn't right, or other parameters that they are in the model that we have to identify them based on all the images we have.
But in these simulations, we try to keep it all the
because
same.
I didn't want to make it so complicated for Rachel.
Mhm.
I keep all the parameter constant. That's why, for example, for this example, you see this garbage result.
Mhm.
These are garbage. If someone tell me, okay, if someone told you that, okay, I designed this is very good system, just
Yeah.
laugh at it.
Even though
Bad
it's-
system.
Yeah.
All of this should be zero.
Mhm.
Has to be zero if the system is good. But we keep all the parameter in normalization, in model, constant for this project, and just let's see that, okay, what is the initial result.
Mhm.
And this initial result is good. Why? Because when I see this, then I will understand, okay, between which mode system might get confused. Then go look at that mode and try to, normalize the system better.
That's fine. So yeah. So we're saying that's the difference between the training and the validation accuracy, and this is why we're doing this experiment, so we can be able to see where the machine's getting mixed up and what can we do to fix it. So, as you can see, a lot with LG03, the one thing I did notice is since it was different than all the other like test experimental data that we did get, it always got it right no matter what, just because it looks completely different from all the other ones. So,
Yeah, because we got all the images twice.
Mhm.
Once we got them with one set of experimental and
Mhm.
one specific focus. So, but the second time we couldn't, we got lost, we couldn't get all the images. So for this experience, we just decided to use the old
yeah,
one
the old one for the
but that
LG3.
one was valid, but wasn't 100% same as the others.
Mhm. So that's why I think the machine was able to pick up the big
Yeah, it was
difference.
color is different.
Mhm. And experimental O3, and as you can see, it's pretty accurate. It got confused here just because the rings were a little bit closer, but it was able to identify what is what. So now we have the simulation 9, which is all of them in mixed up together, and we put 100 images for each of them, so they would all have a good, like, it would be a good number, so like everyone has a fair shot. And as you can see here, it was pretty good for these, and then it started to slowly get a little bit funky. And LGO1 was very, very strong about, okay, I think it's LGO1. So yeah. That was the project. Any for the acknowledgement, I want to thank Dr. Veronis and Sephora for helping me with the project and everything, support and guidance, and this was also funded by the National Foundation.